Well, welcome back, ladies and gentlemen. So we will continue with our morning session here at the Sensor and Test Forum. Our overall topic this morning is calibration. And actually, we will stay with the same special topic, which is frost and dew point calibration. And I'm very happy to introduce our next two speakers, which is Dr. Andreia Furtado and Georg Haschke, both from Process Insights. But you're both working in Germany, actually. Yeah, that's it. So, okay, have fun and stay tuned.
So, it's okay. Hi, good morning, everyone. Yes. Hi to the audience. Thank you for the presentation. So yes, we are coming from Process Insights, and today we have a very brief presentation on first about the lab, Process Insight Calibration Center, mainly about humidity calibrations, primary and comparison methods, and then my colleague Georg will explain a little bit overview about the shield mirror technology and also new products. So as I said, we divide this presentation in two parts. In the first part, like all metrologists, of course, we want to have a look on what is the importance and impact of humidity measurements. Then, of course, we need to look at the pyramids of metrological traceability. And then in the second part, we will have a look inside the PI Cal lab about the calibration measurement capabilities, our methods, the main contributions for the uncertainty, and then my colleague Georg will proceed with explaining a little bit about the shield mirror working principles and also our new product for chamber evaluation, CV180. So I guess that at least 50% of the owners really know better than me why it's important and what is the impact of measuring humidity. So, but for the ones that this quantity or this new field, or this is a new field, why is that so important? Why does it matter to measure humidity? So we know in our daily life that humidity directly influences a wide range of physical, chemical, and biological process, oxidation, so many things that we are seeing everywhere. And so there is impacting significantly the quality of the product, the production efficiency, the safety, the cost, the climate, the health, and the human comfort. So here in the middle, I just left some examples. Pharmaceuticals, for instance, the shelf life of drugs in semiconductors industry, for instance, to prevent the corrosion during the fabrication. And also, if you think about meteorology, of course, that they rely on the measurement of humidity to forecast, or also for the models, of course. So, but this is, we know it is important, we need to measure. But if everyone is measuring in a different way, then we have a big problem. So that's why it's so important that all the humidity measurements need to be reliable, consistent, comparable. So metrological comparable, it means that they need to be traced back to SI units. For this, of course, people that are doing these measurements need to be competent and need to work according to quality systems. For instance, ISO 70025, they need to rely with technical guidelines, for instance, DKD. They need to calculate their uncertainties according to the recognized documents for that. For instance, European accreditation or the guide from BIPM and so on. So this is the only way that we can compare and have comparable results. So for all the metrologists, I think this is the first thing that when we open our eyes, this is what we see every day. We open the lab and we see where are we, okay? So in the very top of this pyramid, we have SI units, so the 7 base units. Who is taking care of this is BIPM in Sèvres, Bureau International de Poids et Mesures. So they are taking care of maintaining the world's standard units and also take care of disseminating this to whom? to national meteorology institutes and designated institutes. And each country has one, and they are taking care of the national standards. And for this, they need to realize these units through the primary realization. Okay? In the case of the humidity, the quantity that we are now talking about, we can do, okay, I put here these two processes, but we can have gravimetric methods and then humidity generators. From gravimetric methods, what we do is to generate and measure a specific amount of water vapor in a gas through mass. So this is weighing method. Or if you use a humidity generator, then you measure the saturation vapor pressure under certain conditions of pressure and temperature. Of course, we need to disseminate down to this chain through some transfer instruments. And what is being used for several years now is the shield mirror hygrometer. So I think you all know it. And why they are being used? Because they are very stable, very reliable. So they are used to trace these units to the accredited labs, and then these labs use this reference to calibrate all the other instruments with different measuring principles. So the uncertainty is coming, so it's getting higher if you go low to this traceability chain. I just leave, you have some images that I put it there, but I found it very useful if you are not used to work with NMIs directly, because if you're working with an accredited lab, you go to the accredited body and you look for the CMCs and you see the uncertainty there. But if you are working with the NMI, KCDB from BIPM, so it's the correspondent database where you can find all the CMCs. So if you look there, it's very curious to see all the countries in the world and their capabilities for measure the humidity. So go there, I think it's a good exercise, and also compare with the calibration labs. So given this, now we are back to, I will invite you all to come to Fellbach to visit us. So, and to present first, and I need to talk about the most important thing in our lab. Of course, it's not in the top, it's in the bottom, people. So we have a great team of very competent people. We are there in Fellbach, 10 minutes from Stuttgart. And of course, then in the top, we have accreditation, DAX accreditation. So we have accreditation for thermodynamic quantities, frost and dew temperature in the wide range -90 up to 95 degrees, primary and comparison methods, relative humidity from 1 to 98% relative humidity, from -40 to up to 125 degrees Celsius, also both primary and comparison. Temperature, have ice point and comparison methods. We recently extended the range down to -80 up to 200, and also decreased the uncertainty in the liquid bath. We can go from 10 to 17 millikelvin now. And this is very recent. We are also qualified or accredited to calibrate DC resistance measuring units or devices in the range of 5 to 350 ohm with a quite good uncertainty, 0.42 up to 3.2 millikelvin. So we are able to give traceability to all our instruments, T12, if you know, this temperature measuring bridge, and this new product that my colleague will introduce you. So, why I waste so much time to explain all these parameters? Just I will explain you that in the top, BIPM, NMI, and then accredited labs. So we are very proud as accredited lab to also to perform primary methods for the realization of humidity. So you are expecting, so we are sometimes in the same uncertainty level of some NMIs, or sometimes even better. So just to give you a quick overview in our uncertainty, measurement uncertainty. So this is the example for the calibration of a shield mirror hygrometers. Of course, if you are using a different hygrometer for relative humidity, then you have higher values. But for the primary values, we are able to achieve 30 millikelvin up to 0.4 Kelvin in the dew and frost, and humidity 0.10 to 0.39. So this is our best method, primary method, so direct, traceable to the SI units. Another service that we also provide there, but this is a factory calibration, just for your information, we perform SF6 gas analyzers calibration, and we are working on extending our accreditation scope also to include the pressure capability up to 10 bar, absolute. So, just to give you a brief overview, and there are some people there in the audience that could explain this much better than I, but I will give you my best. So what we have, why we are able to get such low uncertainties, because we have the primary calibration methods in the lab divided by two range, low and high range. So we are using the saturators. The saturators were developed by the previous Swiss designated institute, MBW. So I have the reference here. And for the low range, operating from -90 up to 20 in two pressure. We have, so this is the schematic diagram, and it's basically first a heat exchanger coil, then you have 18 stacked trays where your dry air is flowing and getting saturated with water. So this is saturated over ice. So the temperature, the frost temperature is corresponding to the temperature of the saturator. I will show you in the next slide the entire setup. So schematic, of course, not a picture. So what is important here, of course, if you want to be traceable to SI, you need to measure something. Of course, we are measuring temperature, so you have inside here, so sorry, this is my not so good representation, but we have two PRTs, platinum resistance thermometers, that they are crossing the saturator. And also we need to measure what? Pressure, of course. So pressure at outlet of the saturator. So we have a 20 bar transducer, pressure, ambient pressure, and also to measure the pressure drop at the unit under test. Okay, so to achieve this low temperature, we have the saturator inside the bath, ethanol, and the flow is every time the same. We have 1 liter per minute by using sonic nozzles. Of course, every time you use primary, we need a monitor instrument. We use a 373 LX. I think some should know this. Okay, so in the hot side, we have we call it a high range saturator. This time it's a 2 temperature, 2 pressure, or 1 pressure, depending on the dew and frost range. So if you are going frost, -20 up to 0, we are operating into pressure, and up from 1 to 95 is 2 pressure. So here is the schematic diagram of our saturator. So the principle is the same. First, we have this coil, and then, so this is the main saturator. I will explain you later the full setup. So when we have the 2 pressures, we are operating with expansion valve, and all the lines are here heated plus 30 Kelvin than the preset. Okay, so this time the saturator is inside the bath. It's not an ethanol bath, it's a water bath because of the temperature range. So, and below we have a preset that is programmed to be 5 degrees Celsius higher than the desired temperature. Then again, we need to measure the temperature of the saturator. Then we have also 1 PRT crossing the saturator, and another one in the bath for control. Again, we need to measure the pressure. So 20 bar or 3 bar, then depending if you are going to 2 pressure, we need these 2 pressure sensors, and then ambient pressure. So of course, all the compressed air, it needs to be clean from oil and very dry. All the lines are made of stainless steel. To achieve this level of uncertainty, I just put there the numbers that we have. So the stability of the bath and homogeneity of the bath, 2 and 3 millikelvin. For the low range, for the high range, we have 4 and 8. How can we achieve also this is to use the PRTs calibrated in fixed points with 5.5 millikelvin, the temperature measuring unit with 1.2 milliohm, and for the pressure we have 0.3 hectopascal, and for the 20 bar 0.8. Of course, when I'm talking about this U total, it includes the drift, it includes resolution, hysteresis, all these sources that we need to add. So it's already included in this total. Very briefly, to our secondary comparison method, I think it's very easy to understand that we have one reference instrument and a second one, then we compare the results. Of course, we don't need the primary generators, we can use commercial ones. And when we are calibrating relative humidity, we are calibrating at the same time the temperature sensor inside either a chamber or a bath, depending on the type of calibration. And to finish, and just to give you an overview of the main contributions for the primary and comparison methods. So in the case of the primary, for the reference, what we have as a main contribution is the saturation efficiency and stability of our saturator, the temperature inhomogeneity of the saturator, determination of the temperature and the pressure, of course, the pressure drop, the correlation between pressure and temperature measurements, and also the uncertainty that is coming from the formula. When we are doing relative humidity calibration, we need to add also the uncertainty that is coming from the homogeneity and stability of the bath or the calibration medium. In the comparison method, the main contribution, of course, is coming from the reference, pressure drop, and the flow. The same for relative humidity. And from the UT, so the unit under test, the basic ones, repeatability, resolution, pressure drop, and flow dependency. I will leave you the reference, and that's it from my side.
Yes, thank you, Andreia, for the perspective from the lab point of view. And may I ask if I also can go on this side for presentation? Yes, it's more comfortable to me. Now we want to go for the application side point of view. I am also part of the MBW brand team. I am taking care for applications and service. And now we want to focus on chilled mirror technology and how it is used for climate chamber calibrations. So our chilled mirrors, here we can have an overview how they generally work. So from the physical point of view, the basics are that we have a vacuum chamber and we put a liquid inside. Here it's water. Based on the temperature of the water, there will be moisture also evaporating to the gas above so that we can measure a pressure. And at the dew point temperature, this is a fixed value. So we have temperature, pressure, and the absolute content of H2O fixed together. So if we measure the temperature here, then we can give, if we know the pressure, we can give, then we know also the absolute content of water in the gas. So how we do that? Since we are talking about the temperature of water, our measuring head is built based of two components. I want to split in two components. We have one the temperature controlled part and one's the optics. And what we do, we give the sample probe, which we want to measure the humidity. We let it flow over this surface, which is temperature controlled. and we cool down with a Peltier this surface until we reach exactly this point where we have fully saturated, where the temperature is that low that there is water on the mirror, and this is detected then from the optical system, and by stabilizing the water on the mirror to a fixed height, we can then know the temperature, the dew point temperature. So with knowing the pressure, we then also can give the absolute humidity content. So how do we use this measurement principle in use cases? So there's one big use case for chilled mirrors is the calibration of climate chambers. And climate chambers calibration is standardized in the DKD R57. And as we have our lab calibrated, as Andreia just shared, by DIN EN ISO 17025, we are close connected to these norms. Talking about climate chamber calibrations, it's useful for orientation to know the keywords about the interior volume, useful volume, the measuring location, and reference measuring location. So you need to orient, and you have to define the chamber and the locations to be able to give a representative value. And so yeah, by chamber calibration, if it's set up correctly, then you have a representative measurement for the chamber. And just mentioned here, for testing purposes, we have other norms, or climate chambers are mostly used in the electronic industry. For instance, next to the lab, so the DIN EN IEC 668 is giving testing instructions and standards to give information about the product safety, lifetime, and quality. So to calibrate, if we have a climate chamber, it's important to know that we have spatial variations of temperature and humidity. We need to define them to find the representative value for this chamber. So we have the total chamber volume, and then we have the useful volume, which we can see as this is the one which will be represented after the calibration. So not the full volume is calibrated, but the one which is defined here. Yes, and therefore we have fixed points defined in the standards where we have to locate our temperature probes, and where we also should place our humidity measurement accordingly. And the second thing which is important, so this was about where to put the probes, and the other point which is important for the next slide I want to present is the stabilization time. When we have a climate chamber testing procedure, it's split in two parts. The first one is a stabilization time, which needs minimum 30 minutes. Is defined to be minimum 30 minutes, and then we have the measurement time, which also is minimum 30 minutes. So this is important for the application we want to introduce, which is a new opportunity for working with climate chamber calibration. So how were climatic chambers calibrated till now? What was the available equipment for that? Usually there was used the chilled mirror, as we have here a 473 SHX. And then you needed the temperature probes, so that you in your climate chamber can spread to the useful volume, which will then be also represented by your measurement. So in the past there was a lot of equipment, and the measuring head was placed inside the useful volume, which also caused thermal loads and effects on the measurement results. So there is a new solution from MBW, which is called CV180. You can see here that it's only one unit with a measuring head. You can attach up to 10 temperature probes and also the chilled mirror to it. So it's simplified solution for climate chamber providers. They were urgently asking for such a solution to be able to work faster in their processes and also more reliable. So what opportunities we now have with the CV180? We need the useful volume represented by the temperature probes, which you can see here, so that we can find a representative value for the temperature, the average temperature value, which is provided by the chamber control. With the spider, this is a spider solution to take care for the temperature probe location. You can extend and lower the distance here between 30 and 60 centimeters square, so that you can applicate it for different climate chamber measures and different useful volume requests. You have a thermal decoupling of the probes, and yes, this is a representative value for the temperature in the chamber, which is then also applying to all the tests which are made. And the CV180 measuring head, what is that now the big change, is not anymore in the chamber as it was here, but it's applied from the outside. So we rebuilt our measuring head, we re-engineered it so that there will be no thermal loads anymore in the chamber, influencing the conditions of the chamber. So we have a maximum flexibility on where we take the probe. As you can see, there is a connector where you can add a tube. So you can, for instance, when you do electronic testing, you have a big test, but at a specific point you want to know the humidity content, as this is a significant part of your technology. Then you can also get the probe from this location. So you are maximum flexible and that you have the thermal decoupling. And as already told, the temperature measurement will also be directly possible with the unit, which makes it easier for the user. So another big benefit of this product, why it was requested from the users, is chilled mirrors. They are working, as already said, with the surface, which will have dew on it, so liquid water. So in case of pollution, it needs to be maintained by cleaning the mirror. And in the past, the mirror was inside the chamber. You need to open the chamber to maintain the mirror, to do the mirror cleaning. So your process need to start again. You need to do 30 minutes of startup time and 30 minutes of measurement time. Now you can see the measuring head can be dismantled outside of the chamber so that we can do the cleaning without disturbing the conditions of the chamber itself. And on the right you can see the probe which were developed. As we are working with climate chambers with high humidity, they are water vapor resistant, and also there was this connector. There is a built-in smart chip which allows to store the coefficients. So in case you have 10 or 12 temperature probes and you need to get all the values in the unit, then maybe one temperature probe fails or is missing, then you would need to type in new coefficients. This solution allows to plug the probe in, and the coefficients will be read automatically. So let's first have a look at how the CV180 measuring head looks from inside. Generally, we have, again, these two parts. The first part is the optics. You have the LED and the photodiode, and the second part is the thermal control to have this surface to a certain temperature and to get the dew point temperature reading. And what you need as well is to get the sample from the climate chamber to the mirror. So in the sample pass, we have included in the outlet a pump so that we can, so that the measuring head is able to work. And as you can see here, the climate chamber heads here, this part is not in the climate chamber, and all the heat load, which is done by the Peltier element, which is heating and cooling, is outside of the chamber. Also, the cooling of this part is outside of the chamber. So, in generally, it can be said that the re-engineering reached the same specifications as we had with the solution before, with the measuring head inside the chamber, which was the 473 SHX. And the range which we can measure is a dew point from -30 to 95 degrees Celsius. If we go for frost point in the specifications, we define it by -27. And relative humidity from 2 to 98%. And temperature based on the type of CV180, there is two types. The one type is for the full climate chamber calibration, and the other one is called CV180 ST2. It will have only two temperature probes, which will then represent the chamber temperature and one for radiation correction. So you will have then only two temperature probes. So this was an overview of the climate chamber calibration itself. Let's have a look at the key benefits and probable further opportunities for development opportunities for the users. So there is now a smart device available which will automatically load the coefficients, so you can work fast with this device in climate chambers. You can do the mirror cleaning from the outside, so you don't need to open the chamber. This might, I'm just having the thought in the moment, something if you have health risky substances which you have in the chamber, this could be a new opportunity and solution for that. But there's also others. You have an easy setup and robust design, and the thermal load of the chilled mirror is now, as said, not anymore inside the chamber but outside. So you have no thermal influences. The flow of the chamber is of a higher quality, representative also for the test scenario. And the CV180 in the software also has an automatic resume of measurement. So after you clean the mirror, or if you set up the mirror and you want to measure, it will automatically start up, which was before done by hand.
Sorry.
And this is some input from the application and service side.
We would like to thank you all for interest, and we are open if you have any questions. And sorry for having you some minutes more.
No problem, no problem. Thank you, Andreia. Thank you, Georg.
Thank you all.
Yeah. Are there any immediate questions from the audience? We have some spare time before, I guess, our next speaker is just installing itself. You can already approach our technician if you want. Don't be shy. No, not at the moment. So I think if you need more information or you have questions indeed, then you can contact the guys at the booth. It's 537 537. I think it's somewhere in the area here, not too far from here. Yeah. So.